Yeah, so Adit is currently pursuing his PhD at Cornell and is right now PhD research intern at Adobe Research. His research interests are mainly in theoretically analyzing reinforcement learning and online learning method with an application focused on ML systems. Over to you.
Thank you, Naman, for the introduction. So, hi everyone. I'm Adit, and I'll be giving today's talk. The talk is on controlling distributed optimization from a stochastic oracle. Uh, just give me a second. Just a second. Yeah. Uh, so yeah, it's about controlling distributed optimization from a stochastic oracle for different applications that I'll be talking about. The talk is divided into 5 parts, and each part will roughly be around 10 minutes. But feel free to interrupt me anywhere in the middle if you have any questions. Other than that, of course, I'll take a pause after every part so that I can address any questions. And there can be a Q&A after, depending on the time. Uh, so yeah, most of the work that I'll present today is done in collaboration with my advisor at Cornell. Yeah. So let me start by giving like a broad overview of what the problem setup is, and then I'll delve into like what the mathematical formulation is, what was the motivation behind it, and how do we solve it. So here's the overview of the problem. The problem is basically the setup of oracle-based optimization, where some learner, so for example, this is an example of pricing optimization, where a retailer who is a learner can actually ask questions. Here the questions are like yes or no questions, and to an oracle, the oracle replies no or yes with some confidence. And the oracle is such that like at different time points it has different confidence in how it can reply. So the state of the oracle is stochastic, and the confidence varies over time. And now the retailer wants to optimize the price that they want to do. So here they are doing a binary search kind of optimization. But they of course want to make sure that the answer that they eventually end up with is with high probability the right answer. uh, so that is the overall setup. uh, like taking it the other way, we basically have the oracle has different states. So let's say the green is the good state and red is the bad state, and its state varies over time. Now, if I were to give you the oracle states in well in advance, like you know all the states that are there, and you want to ask 5 questions to the oracle, where would you ask those? Sorry, 4 questions to the oracle. Where would you ask those questions? You would ask those questions at the right or the good instance. But the problem is, ideally you would do this, but you don't know in advance where exactly are those good states. So the oracle is in a good state if it replies with like high confidence. In this illustrative example, I'll define a good state like more concretely, but good state is when the oracle is confident about its responses. Sorry, yeah. Yes. Yeah, like how, yeah, it's basically the probability with which the answer is correct. Uh, you can, so let me go to the like the application where this is used. But yeah, anyways, the point is that you basically want to exploit, you want to impose some structure on the stochasticity of the oracle, and then exploit that structure so that you are able to, in real time, actually take decisions on if you should query the oracle or not, based on what exactly the state of the oracle is right now. Uh, so what is the structure that we basically impose is that we say that that is the underlying theme, that this transition from a good or bad to a bad state is Markovian in nature. Of course, we generalize it to like a multi-state oracle, and like, I mean, but the overall view is this. So yeah, let me go to the math of it. Uh, Basically, the learner aims to optimize some function and obtain like a minima of the function by querying an oracle. The learner queries the oracle at some point and receives a noisy gradient back from the oracle, right? Uh, I'll tell the assumptions on the function and noise in a bit. But basically, ideally, the learner in a first order based optimization setup would use these noisy gradients to update its estimate iteratively and eventually expect to arrive at some minima of the function. Uh, the thing is that this noise in in this particular first order optimization case The variance of the noise we assume to, like in general, it's assumed to be constant throughout, and there is a bound that literature assumes on that variance. But what we assume is that that variance could vary over time due to like motivation that I'll present next. But now we want to exploit this variation in the variance, and we want to basically optimize when the variance is low enough. Yeah. Of course. So it is, so that confidence thing was basically an illustrative example, but it is connected in the sense that the variance is, like if the variance is low, the confidence in the gradient is high. But it like, so I don't use confidence intervals especially. Like I only work with like noise and the variance associated with it. That was an illustrative example. Yeah. So basically, this is the motivation behind it, where like one of the motivations behind it, where in federated learning, you basically have a central model which is optimized by querying uh, like client devices who have some local data on them, and they provide you with like an aggregate gradient for some weights that you send to them. So basically, it's a like federated learning. You have some iterative mechanism which optimizes the global AI model. The global AI model is optimized by querying the weights to the devices. The devices optimize on their local data and then return with some aggregate noisy gradient at that particular point. So the bottleneck here is, of course, that the compute is limited. And also the devices that are available at each point in time is different. So basically the client participation varies over time. And what we assume is the client participation is Markovian in nature. So the oracle in general, if like there are a lot of clients participating, then you can actually say that the gradients have less noise in them. And if there are like more clients, less clients participating, the variance will be more. So you would ideally want to optimize when the client participation is more and the oracle is in a good state. And so this is the motivation behind like the oracle being stochastic, where your clients are not exactly in your control and they participate with their own, like some probability each client participates. So the net oracle is stochastic. So how do you control the communication of the learner? How does the learner choose at what time points they should learn so that the learning that occurs is robust in nature? Yeah, so there are different things that vary over time. I just talked about the availability of the clients, but the resources that they provide and the quality of the data that is there at any point in time also varies. Oh. Yeah, ideally want to learn when the oracle is good, otherwise skip. Yeah, so now we basically have a moody oracle. We have the quality of the gradient varying with time because of heterogeneous data. And we like the noise, basically the quality of the gradient is what we quantify with the variance of the noise that is added to the gradient. And this is assumed to vary over time. So it's sort of the variance of this, sorry, the bound on the variance of this noise varies over time. And we basically take an assumption that that variant, like that variation is Markovian in nature, which is like a, let's say a stronger or a weaker assumption than taking it to be same throughout. Yeah. What is the existing work that has been done? I think let me just check the time. Yes, I mean, so there has been some existing work done in this field where people have proposed different federated learning mechanisms and various reinforcement learning approaches. But the approach that we take is perhaps of modeling this query-based optimization as a Markov decision process is slightly different than the existing work that has been done here. And it can actually be extended to different federated learning algorithms, which have already been proposed, for example, scaffold. So now let me move to the problem formulation. Before I move, any questions? Okay. It is when the variance is small. Yeah. Sorry. Yeah. So basically, the response, the oracle receives a query. Yeah. The oracle receives a query Q, evaluates the gradient, and adds some noise is such that at time k, it is bounded by some constant sigma k square. Right now, we assume that when the oracle sends back the response, it sends us the response and the bound on the noise variance. So we know both sigma k and like the response, of course, you'll know, but the sigma k is like this is sort of a strong assumption that we make. But in practice, you can actually take some proxies for like substituting for we know the sigma k that is received at every point in time. And secondly, so this is a typo, but anyway, so there is some probability which this sigma k will be less than some sigma chosen by the learner. So the learner has a threshold on what is its quality that it can accept the gradients below. So if the noise variance is below a particular threshold, then it can accept that gradient. Otherwise, it won't. So there is some probability with which it accepts that gradient. Uh, AK is basically the action of the learner, and the action, I'll discuss that in more detail, but for now just consider it as at every point in time the learner either decides to learn or not learn, and so the action is a binary action in that case. And of course the learner will only receive a response if it actually queries something. What is the objective of the learner? The objective of the learner we consider is that it needs to get epsilon close to a critical point in expectation, because we are dealing with like a noisy first order gradient descent method, and the assumption that we make on our function is just that it is like we don't make any assumption on the convexity of the function, or let's say the existence of a global minima. All we care about is that in finite time we should at least reach an epsilon critical point with like in expectations. So that's not even with a high probability. The expectation is over the sources of randomness, mainly here, which is the noise. So the noise is varying over time. And of course, so if you have a stochastic policy based on which you are querying or not querying, the expectation is also over that. You also? Yeah, sigma k is a random variable, which varies over time. And that is what we assume to be like to reflect like that is what we assume to be Markovian in some sense. Like sigma k is dependent on the oracle state. Does that make sense? Yeah. So like in theory, we just assume that there is some sigma k that is given to you. But in practice, there are proxies. So for example, you can consider sigma k to be the number of clients that the learner has a threshold on, and at each point the number of clients that is participating is varying over time. And so now the learner has a threshold on what is the minimum number of clients they need. So sigma k can then in that case also you can so in that case can be considered as the number of clients. Also for this noisy gradient, you can actually, for simple models, you can actually like explicitly like characterize the equation between sigma k and the participation of the clients, like how much is the variance depending on like how many clients are participating. Ideally, if you have like infinite number of clients, the variance will be very low. Like you will get the exact average because that is the expectation that you want. But yeah, so that is, you can assume it to be inversely proportional to the number of clients. Yeah, does that answer your question? Yeah, the variance bound is changing, yes. So no, so this is a condition that we need to satisfy. This is a condition that you need, like this is the objective of the learner. So you need to learn an X hat. So you need at the end of, let's say, N rounds, you need to have an X hat which satisfies this condition. And so you will need to learn according to that. Of course, in a stochastic system, there is a chance that, let's say, if you always have a bad state and your policies is that don't learn in a bad state, you will never learn. So your X hat won't be like this. But you need to formulate the problem such that your stochastic system, like the problem formulation is such that this objective is achieved in finite time. And that is what we'll come to next. So sigma is a parameter. Yeah. Sigma is a parameter that we choose as a learner, but you can also optimize for the sigma if you have the other parameters given. So the next slide is the explicit relation between sigma and like the number of queries that you need to successfully learn. Anyways, any other questions? Yeah. That process, as I move towards the end, like right now we assume it is given, but that is something that our stochastic approximation learns, like the parameters of that process. Not in closed form, but like our policy is such that it can learn, implicitly learn those parameters. The number of steps that I have to take. Yeah, so like that is what I'll move to the next slide. But we basically characterize the number of steps that are required such that this is true in expectation. Like the max, there is a bound on that number of steps. And the question is there a fixed number or is that like a strong? No. So there's we work under the regime of fixed number of steps which we calculate. Next. Any other question? Okay. Uh, Actually, very good questions. Sorry if I rushed through the questions, but so basically, yeah, the assumptions that we make on the function are pretty standard in first order optimization methods, which are basically that the function is bounded from below, continuously differentiable, and is Lipschitz continuous. And like the noise is such that, of course, it is zero mean, and it has like it is bounded by some sigma k, which is like returned with the response. I'm sorry, the arrows are because I prepared this in another presentation software. I think in PPT they have, but anyways, so yeah, so you basically have some estimate which is updated iteratively. Let me just check the time. Okay, so which is updated iteratively by like this is the standard SGD update. I hope there are no questions about it, but so there's some step size and the response is used to update. What we propose is controlling this SGD. So we basically have some estimate which is updated, but only if two conditions are satisfied. One is that A, the learner actually decided to learn, and B, the response was good enough. How do we decide the response was good enough? If the sigma k is less than equal to the sigma squared. Like so if if the variance is actually bounded well in, like good enough. So those are the two conditions which we use to characterize learning, like updating our estimate. So you ideally want that both of these things happen in conjunction, that if you are learning, you actually receive a good response. But of course, since this is a stochastic system, there is some probability with which this will happen depending on the oracle state. But you ideally want this to happen like more frequently than not. So yeah. So basically, we characterize a successful learning query if it is indeed a learning query and if the response is good enough. Let me actually pose the theorem. So you basically have a successful update. Now, how many such successful updates you need so that the objective that I presented, which was that expectation of the critical, like the gradient at the estimate should be less than epsilon, is like the number of such successful steps required is this. So epsilon is the parameter of how close you want to be to the critical point, and sigma now here is the tolerance that we set. So now your m is decided by some sigma which you choose. But so that is, I think, oh, I missed that point. Yeah. No. So AK is one if you actually AK is the action of the learner. So you decide to learn. No. So the thing is that there are two things there. One is that you have to actually query the oracle, which costs some, like which incurs some cost, and then the oracle sends you out the gradient and the sigma k. So now, if the sigma k is good enough, you will actually update your estimate, right? But like you have already decided to learn or not before that. So your policy should be something that decides to learn if it is sure that. Yeah, so that is the entire point. Like we want to reduce the number of queries that we pose. Sorry if that was not clear. Yeah. Okay. So now, yeah. So basically, the thing is that.
I have a question. Can you hear me? Calling from
Yeah, I
online.
can hear you. Okay. Yeah.
Yeah. So, just a quick question. So, even if, let's say, the estimators are unbiased, but if this success query is biased, so conditionally, so you do have an assumption on how many times is the update successful. But if conditionally, let's say for some type of some directions of gradient, say, there is a very large number of queries that get rejected. Would that lead to a bias? Sorry
Okay.
if the question is not clear. I'll repeat that.
No,
So, are
go on.
there any assumptions on the conditional success? given the state?
Given the so given the gradient, are you saying
Given the
that
gradient,
like
yes.
is my success of the oracle or success of this particular, let's say the response is good enough, depend on my gradient where I am currently, where I am currently and what my gradient is?
Yes, and specifically, let's say certain directions of gradients always fail. Would the algorithm still work? With the theorem still work?
No. So just, I mean, let me, maybe I'm not being very accurate in what I'm saying, but the model that we assume is that the grade, like the response is the gradient plus the noise. The sigma k is just on the noise, and the noise is assumed to be independent of the gradient. So whatever your gradient or the direction
Noise is
is,
independent. Okay, understood. If the noise is independent, then it works. Okay, thank you.
the noise is assumed to be independent of the gradient, if that makes sense.
Yeah, thanks.
Okay. Yeah, basically, so now the question is that we need to perform m successful learning queries in n total queries. And this is the problem statement that we have. How do you dynamically query the oracle for m learning queries in n total queries such that the learning objective is achieved and the communication cost is minimized? So at every point, we have the choice to communicate or not, to like send a query or not. And at every point in time, we receive like a successful response or not. Now, the reason why we need this successful response is to have a fixed number of points or fixed number of queries that we want. One thing is that if like you might say that, okay, let us just reduce the sigma because sigma is something in our hand and we can like get away with like a small number of successful queries. But the point is that if you reduce the sigma, then the probability that the sigma k is less than that sigma also reduces. And so now you will have less number of successful queries to actually get away with. So more number of queries will fail. So sigma is a parameter that of course can be has to be chosen correctly so that I mean, this is something that again can be optimized for, but right now I assume that this is a parameter that the learner chooses. This and epsilon are the parameters that the learner choose. So this is the thing, like the problem statement. And one last thing is that we this is a system assumption that we make, that we basically have a queue of ML tasks that central learner has to perform. So the central learner that I presented has to perform, just a second. So this learner, this FL learner has to perform some tasks with the Oracle. And we have a queue of those such tasks that, sorry, yeah, like so a queue is maintained and each task is of the order m, the order that we calculated. And you basically the learner has to query these number of times for one task, then these number of times for the second task, and so on and so forth. And there is some arrival probability of the ML task. This is a system assumption just to extend our work to like real life settings. But yeah, okay. So I'll move to the solution framework. I think I'm doing okay on time. Is there any other question regarding the problem formulation? Is the problem formulation clear? We can spend more time on it. I think the problem formulation is more important than the solution. Okay.
Quick question.
Yeah.
I was wondering whether these M tasks are randomly arriving or the learner can make a choice on the task, like they want to learn
right
from.
now we assume that there is some arrival probability with which these tasks arrive. These are not in the hand of the learner exactly. Like these can be retraining tasks or training on a new context. Like these are given by the
Understood.
external environment to the learner.
Second question, would the algorithm that you propose also possibly output the sigma? Because there seems to be some variation with sigma on the convergence rates.
Yes, exactly. So to frankly answer a question, no, the algorithm that I am proposing is not really considering like the optimal sigma that will be there. But that is something that like that is a sort of the next step to the algorithm that I propose, if that
Okay,
makes
okay.
sense.
And even so, like it may only affect constants, is it? It may
Yes.
not affect the order. Okay.
Yeah,
Fine.
yeah. I don't think it will affect the order. But yeah, it will definitely affect the constants. Okay. So now the
Thank you.
solution framework. Yeah, so we basically consider a constrained Markov decision process formulation of this problem, where we have the standard recipe items for the Markov decision process, we have a state space which has the oracle states. So we discretize the oracle states into some k states. This k again is a variable that you can choose, which will change the oracle transition probabilities. I mean, this is for now, assume that this is there. Once I present the algorithm, it will be clear, like the choice of k is something which is more dependent on how fast you want the algorithm to converge. But yeah, so oracle states can be, is there. The Q state indicates the number of learning queries, the successful learning queries that the learner has to do. So this is the M that I just had discussed about. The action space can either be a binary action space where you either decide to learn or not learn, or you can also decide not to learn, or perhaps even incentivize the oracle. So you can provide different incentives to the oracle. If the oracle is incentivized more, then the probability that it will, the sigma k will be less than sigma will be more. So you can basically bribe the oracle in some sense. Like these setups are also very popular in the federated learning setup that I talked about, where the client is incentivized to participate. But yeah, the binary action place is also there. There's a stationary policy over the state space to the probability simplex of the over the action space. We have the costs. So there are two costs. One is the learning cost, which you incur because of the action of communicating and then learning. So each query that you pose imposes a learning cost. And there is a queuing cost, which is incurred if you have like a queue of a certain size. You incur that cost based on, like, this cost will increase with the queue size or the buffer size, because you don't want your queue to remain long enough for. So these are two contrasting costs in some sense. Uh, so, and then finally we have an oracle transition probability, where in the current state of oracle, with some probability you transition to another state of the oracle. Right now we assume knowledge of them, but the final algorithm that I present doesn't need the actual values of these transition probabilities.
Hey, quick
Uh,
question.
yeah.
So on the previous slide, in fact, maybe a couple of questions. So is the queue known beforehand? So is it available at the start of the problem, or is it an online queue?
So so
That's
you have
the
some
first
initial
question.
queue, and then there is some probability with which new arrivals happen,
Understood. But
and
the
some
order of
probability with
the
which
size of the queue does not.
queue gets empty.
Okay. The second question is, there is this action space, but maybe I missed this, but who's taking these actions? Like,
The
who
learner,
has to incentivize
the learner is taking these actions as to whether
not
to query the oracle or not, or whether to incentivize the oracle or not.
Okay, understood. Thanks.
So incentives can be like either monetary incentives or computational incentives that the learner provides to the oracle. Like there are so in the federated learning setup, the clients are incentivized to participate and like give their data or share their data in terms of some services that the client is like the learner is providing to them.
Right. So in any case, so this seems like the policy is what has to be learned, and the policy is a finite policy.
Yeah.
In the sense that the oracle times the queue is a finite set, and then you'll have to learn
So
the
that's
best
a
problem.
good point. I think so. This in general is a countable set, but for the experimental purposes, we have taken it to be a finite set.
Okay.
But
Yeah,
yeah,
because
it's
the
a
queue
finite
might be.
policy. Like in most practical applications, it's a finite policy.
And because it's a finite policy, would you be able to use like tabular setups, or like what is the?
That's a good point, and that is what we will turn to once I present the setup. Where, like, of course, you can use a tabular setup, but then you will have like a dependence on the number of oracle states and the queue state space, which the queue state space can be very big. So your algorithms might be very inefficient. So we impose some structure on the cost so that the policy has some structure, which can actually be parameterized very efficiently. So you won't need a tabular setup in some sense.
Okay,
Does
so
that make
your
sense?
parameterization is somehow more efficient. Yeah, that makes sense.
Yeah.
Thanks.
What is the queue state? The queue state is the number of successful queries that I defined earlier that the learner needs to make to the oracle. So it should be like the queue is on. So that let me just move to the next slide. This is a probability transition matrix for the entire state space, but basically the queue reduces by 1 if you make a query and if the query is successful. So there is some probability this sigma, this gamma is the probability with which if you make a query, it is like, so in oracle state O and with incentive I, that the oracle will actually respond with like the correct probability, or will respond with a sigma k which is less than sigma. Now, of course, again, right now I'm assuming knowledge of this, but the algorithm that I propose does not assume any knowledge of the gamma O comma I. Like that, this is something that. Yeah.
Isn't that the same computation cost as asking a query to Oracle?
No, so the oracle state, see, the cost of asking the query is that you have to transfer, let's say, if you're training a transformer model, you have to transfer 70 million parameters to the devices and then get 70 million parameters back. The oracle state can be very simple, something like how much data is available or how much computational resources are like, or how many clients are participating. It could be like a very simple like communication, which is like much less significant like communication cost than, let's say. So there is some communication that happens at every point in time. I'm just saying that like the communication cost of actually learning is much higher, like let's say orders higher than the cost of just asking what the oracle state is and like any other variable that is of interest.
Hi, I have a couple of more queries. So the
Yeah,
first
go on.
query, yeah. So I'm assuming something. Please tell me if the assumptions are right or wrong. So the learning cost is not known beforehand. Queuing cost is not known beforehand, and neither is the transition probability. All of these have to be estimated as the problem goes on. So is this assumption correct?
No, so the learning cost and the queuing cost in our setup is something that the learner sets up. Like we use some models of cost, which makes sense. But the transition probabilities are not known because they are system parameters.
Understood. So in case the transition probability is not known, are you first, so are you using a model or a model free setting where you're first going to estimate the transition probability and then the stationary policy, or would you implicitly assume the
No,
transition probability?
No. So we don't actually, like, we don't empirically estimate the transition probability matrix. We estimate the policy, and the policy is such that it is optimal for whatever the true transition probability matrix is, or approximately optimal.
Understood. So it's a sort of implicit.
Yeah,
And
it's
it's
like a
a
policy
model free
gradient
setting.
method.
Okay, understood. Thanks.
Policy will only depend on what the oracle state is, and you're always getting update on okay what the oracle is in. So then
Yeah, so that is a very good point. First of all, that is true. That is what we show in the structural results, that if your L is very large, then even in a bad oracle state, like your policy will be something like that. And that will optimally be calculated based on the costs that are there and the transition probabilities that are there. Second point, we also pose, or like, I'll show you so there's a queue stability lemma that we have, so that the queue does not overflow, or the queue is not such that like you have to use such a policy. Like your queue is stable in some sense. So that is one thing. The second thing is that, so the third thing is that, like, I mean, that is something that you like, if it is the case that there is a large number of ML tasks, then you can't create like the task is moot. But what we are cared about is something in between. Like when the task is not too small, not too large, something in between. So can you actually exploit the stochasticity? Of course, you can't exploit it if there is a workload which is like impossible to deal with. You had a question, right? Yeah, it is independent of past actions. So it's Markovian only with respect to the past oracle state, but it is independent of the past actions because that's a good question, because, and something I did not miss to mention, that the oracle transition is independent of the actions. Like you can't incentivize the oracle, and that is a strong assumption to make. Like that should not be there ideally, but that is an assumption we make for the structural results, that your oracle does not steer into a very good state because you're incentivizing it. I would say it's a poor assumption on our case and can be improved upon. But right now we make that assumption. So it's independent of the current action and hence independent of the past actions also. Incentive is something that you give for the current oracle state, and it reduces the probability. So this probability of a success is increased if you have like a higher incentive. So at that point in time, the oracle will provide more data or something. Okay. Yeah. So we have two things. We have the average learning cost and the average queuing cost. Our optimization problem is to find a stationary policy such that the learning cost is minimized with a constraint on the queuing cost. So this answers your question as well. Like we have a constraint on the queuing cost. Your queue cannot be arbitrarily large because you have like some constraint on the queuing cost. So at that point, it will start querying more and more. But if the constraint is like well enough, then it will like keep on querying as it were. So so we have to find the optimal stationary policy such that this optimization problem is solved. I'll move to the structural results. I don't think I have. Yeah, I'm a bit over time. Still, if there are any questions.
Do you have time for one more question?
Sorry?
Do you have time for one more question?
Yeah, go on.
Yeah, so a typical transition probability would be something like O cross A to delta over O.
That is, yeah, a typical would be that, and that would be for the oracle transition probability, not for the entire state. But yeah, for the oracle state, that would be the transition probability.
Agreed. And now you're saying it's O cross O time 201. I mean, this is a small point, but you would have to maintain the probabilistic structure of that, right?
No. So that is just the probability function. O cross O, 201 is the probability of like what is the transition between O1 to O2. This is the function. So this function creates a probability transition matrix over O
this
cross O.
This is basically a matrix. Okay. Yeah. And this matrix is like fixed. It's a fixed matrix irrespective of the actions, and it happens every time.
Yeah.
Okay. Right. Okay. Thanks. I understood the model.
Okay. So now what do we try to do once we have the CMDP setup is that we take some structural assumptions on the cost and the transition matrix, which lead to the optimal policy having a threshold structure. What is a threshold structure? A threshold structure is such that if the state is below something, the state here being the learner queue state. So if the queue is small enough, your action should be like not learn. And if the queue is large enough, or bigger than something, then your action should be learn. And this threshold will be different for different oracle states. So a good oracle state will have a smaller threshold because then in a good oracle state, you want to learn as much as you can. You want to be more greedy in some sense. And for a poor oracle state, your threshold will be higher. And this also basically tells us that this is the intuition or perhaps a side intuition that we have, that you query more aggressively when you are far away from the minima, because the noise does not make that much difference to you. Like you can actually tolerate more noise when you are away from the minima, and you can query more aggressively. That is one point. Yeah. So these are the assumptions that we make on the structure of the probability transition matrix and the cost. These assumptions are in general in this literature called as interval dominance assumptions. And there has been work in economics and both reinforcement learning on this particular set of assumptions. The first assumption, of course, is that the learning cost is increasing and convex in the Q state. This basically incentivizes us to query more because you're incurring a higher learning cost when your Q is larger. Your transition probability matrix is TP3, and also this. This is called the probability transition matrix being supermodular, where you are saying that sum of B dash probability B dash given B O comma U is increasing in B. This assumption and the TP3 assumption is something. Is TP3, and this is increasing in B and convex in B. These assumptions basically, I won't go into the details of that, but these can be proved for if you have like the probability transitions matrix that you have for reducing the state space. So this is the probability transition matrix that I had for O dash B comma. So this can be decomposed into the Oracle transition matrix and the Q transition matrices. So for this particular structure, these assumptions can be shown that they hold like they indeed are the case. Then the Q cost is also increasing and convex in the Q state, which is basically saying that again, if your Q is larger, you'll be penalized more, and so you will be incentivized to act more in that direction. This assumption is the key interval dominance assumption, where this is a generalization of supermodularity, or I always get confused between the two, but I think this is supermodular. So it's the generalization of supermodularity, where you have some constants alpha dash, which is greater than 0 for this, for which the Q, the cost C is satisfied. If we have time, I'll show you the structure of the cost that we assume and why it satisfies this particular assumption. But most, like if you have a linear cost, then this definitely is satisfied. But even for a like quadratic cost, this condition is still satisfied with a alpha which is greater than 0 and less than 1. This final condition is on. So this is a little. So this is basically the notation. I have not explained the notation, but this P dash O dash, sorry, P O dash B dash U plus 1 is basically the probability transition matrix, like the normalized probability distribution for a given transition of O dash from a state B dash to all the states, like all the learner states. So basically, I'm taking a particular row or particular section of the probability transition matrix and normalizing it. That is what P dash is. And this is the interval dominance condition, the convex dominance condition, the interval dominant version of the convex dominance condition on the probability transition matrix. This again is satisfied for the probability transition matrix that I showed you, under the assumption that, which I should have mentioned, but under the assumption that your success probability increases with your increasing incentive or increasing action. So all these assumptions are realistic for the cost that we assume, and the transition probabilities, such as the arrival, like we have an arrival, we have some probability with which that the queue gets empty, that these conditions are satisfied. Finally, there exists some alpha dash alpha is equal to B such that this holds. So this holds true for any alpha less than 1 greater than 0, and this holds true for any beta greater than 0 less than 1. So there is, of course, an alpha equal to beta for which these two hold. Yeah. So finally, we have the Q stability condition that I was talking about. In the interest of time, I would skip this and just state my final result, which is the structural assumption that I have. So under the assumptions that I showed you, the optimal action for the finite, so that like the problem which we formulated was for an infinite horizon. The result that I have mistakenly copied is for the finite horizon MDP, is increasing in the Q state. This is also true for the infinite horizon version of it. But the thing is that this is true for a finite horizon version where you are incurring some terminal cost and you have some running cost. For the infinite horizon version, what we basically have to do is we have to first consider a Lagrange constrained MDP, where you have the learning cost plus some Lagrange multiplier with the Q cost, and then you take the Lagrange constraint, like the Lagrange constraint MDP. The structural result still holds true for this, can be proved for this Lagrange constraint MDP, but the Lagrange constraint is for some Lagrange constraints. So how do we move back to the original constraint MDP? That is through this result from 1993, where they said that the optimal stationary policy for the CMDP that we had is actually a randomized mixture of two pure policies, where each policy is the optimal policy for an average Lagrangian constraint, like cost MDP of the form that I presented. Like this is the cost, and P is some probability. So now finally the point is that we'll now move to the algorithm finally, but the point is that we basically have this some probability. There is like a randomization between two pure policies, and each of the pure policies is threshold in its own self. So the final policy is still a threshold policy because each of them are a threshold policy, but it is a randomization between the two things. So now, since the policy is proven to be threshold in the Q state, you can actually use a sigmoidal representation for the policy and learn the policy using stochastic approximation. The stochastic approximation that we use is simultaneous perturbation stochastic approximation, SPSA, and we basically estimate the thresholds adaptively by like running whatever current mechanism we have, like current estimate of the policy parameters we have, and using the average, like the approximate costs that we incur to update the policy parameters. This is the algorithm finally, where you have some initial policy parameters, some parameters of the algorithm. You basically, this is the standard SPSA algorithm where you choose the policy parameters to be updated, and the policy parameters that you choose to be updated are perturbed by some, let's say, some perturbation factor omega. And you calculate the average cost. The average cost is calculated approximately by running the system for like t time steps using those policy parameters. So you assume like you can actually use the policy parameters for some t time steps. And then finally, you have a delta hat, there's two approximate gradients of the learning cost and the queuing cost. And you basically use those estimates to update your, here the theta represents the policy parameters. So you adaptively update your policy parameters. Why are there two equations? Because one of them is to update the Lagrangian parameter, which basically ensures that the constraint is satisfied. And so this is the Lagrangian like version of the SPSA algorithm. This algorithm can be shown to converge asymptotically to the distribution of the true parameters. Converged almost surely, convergent distribution to the set of like optimal parameters, but asymptotically. There are no finite horizon results known for the SPSA algorithm. Finally, this is something that we did not start with. We had basically, our idea was to like control the SGD that the learner is doing. But now we have a stochastic approximation algorithm which controls the SGD that like the policy. So this determines the policy through which the learner is controlling the SGD. The stochastic approximation, of course, has some benefits to it because now since you're only updating the policy parameters, you don't need any knowledge of the transition probability matrix whatsoever. Secondly, you don't also, like with a constant step stochastic approximation, you can actually track changes in the system. So let's say if your arrival rate suddenly increases, your system can actually track changes in the system. And this is an example of a 2 timescale system where the stochastic approximation updates the policy and the learner queries using that policy to run an SGD and like completes its machine learning tasks. I'll discuss if there are any questions. I can take them, or I can just discuss like the last part of the talk and then we can take questions. Okay. So one extension that we are working on is that what if there are multiple learners that are querying the Oracle one at a time? How do you schedule these learners based on the Oracle state? And how do you control their learning? So the controlling their learning part is sort of the same. The scheduling part is something that we are right now working on a greedy scheduling protocol, such that this particular framework can actually be augmented into a framework which is known in game theory and in like stochastic games as the switching control game framework. So where you basically segment the state space of the learners into disjoint state spaces, where each learner, when the system is in state space 1, only the learner 1 will control the transition probability matrix. So the transition probability matrix can be factorized into like the actions of the current learner when, like, let's say learner L in the state is in SL, and the other learner's state are not like the other actions of the other learners don't make a difference. So this actually has a very nice structure, and under the zero sum or potential game cost structure, it can be shown to have like a threshold Nash equilibrium. So the threshold results or the structural results can be extended to the case of multiple central learners under these assumptions, which can then be efficiently estimated using an SPSA kind of algorithm. Secondly, sorry that my talk did not have any mention of LLMs, but these methods can be extended to the LLM context, where you have a system which you are querying, and that system itself varies over time. The quality of that system varies over time. So it can be used for inferencing from LLMs and stochastic schedulings of different queries that are arriving in an LLM. Distributed fine-tuning of transformers, which is an extension of federated learning. And also it can, this is something that I'm more excited to work on, where if you have, because LLMs or any other transformer that comes in the future, basically at the end of the day gives you some embeddings or a better representation of the data. So how do you control and query those embeddings is an exciting problem. And depending on what you want, which is the state of the oracle in some sense, how do you efficiently query this? Finally, this is the original motivation of the problem, which I have 2 minutes to explain, where we had a federated learning setup, but then our problem was not to learn or skip. It was to learn or obfuscate. So there was an eavesdropper who could actually observe. So every client actually knows what the current weights are, because that is the gradient update that they make on. So even an eavesdropper can spoof as a client and can actually observe your optimization process. And if you don't learn on obfuscate, your optimization process, which is like a minimization, let's say SGD, something SGD, it can just take the last point of that optimization and use it. So those weights can be used for, I don't know, like competitive purposes or even like malicious purposes, where it can bypass your machine learning system using those weights. So this was our original motivation for like controlling the SGD of the central learner, but now we have extended it to like robust federated learning and things. I have some numerical results which show that the optimal policy is actually like as good as a greedy policy in learning accuracy, but does much better in communication rounds and is much better in learning accuracy than, let's say, a random policy. Uses less incentive than a greedy policy, but more incentive than a random policy. So this achieves sort of a trade-off between the greedy and random policy, which is what we intend to do, like what that was our problem statement. This is the convergence of the SPSI to the true parameters, which are these dots. Yeah, so this is my ID. I would love to connect with you. This is what I have worked for the last 2 years on. But right now I'm also interested in like bandit optimization, linear bandits, and even like normal multi-arm bandits. But like if you have, like if you're interested in this work or anything, want to discuss anything, I would love to hear from you. And if there are any other questions. I'll just ask one question, like how many of you at least got the gist of the problem? Okay. Yeah. Thank you for listening patiently. I know. Oh, also finally, I forgot to. This is something I should have done. But this work is based on these works, and so our like one of our work got accepted in TMLR, and the other work got accepted in control system letters. Right now, we are waiting. Like one of them is under revision at NACO. Yeah. Thank you, everyone.